Today we are going to talk about the Mass-Baur spectroscopy. There are few questions they have asked in previous exams. So those questions now we are going to solve. So this is the question number 1. The correct order of isomeric shifts in Mass-Baur spectra of source as given, that is 57 iron of the iron compound. So here 3 oxidation states are given. So now we have to calculate the isomeric shift for these 3 nucleus. So the general formula of isomeric shift del equals to K Re square minus Rg square psi s square minus psi a square. So here Re means the radius of the excited state and Rg means the radius of the ground state. Next, psi s means electron density at source and this is the electron density at absorbent. So as we know that the radius of the ground state is greater than excited state, because the number of electrons in the ground state is more compared to excited state. Because of that reason the radius of ground state will be greater than the excited state. So here the radius of the this is the radius of excited state and this is the radius of ground state. Since the radius of ground state is greater than the radius of excited state, this value will become negative and K is the constant here. So finally isomeric shift del equals to minus psi s square minus psi a square. This you can write as a del, directly proportional to negative value of psi s square minus psi a square. So now as we know that isomeric shift value is inversely proportional to s electron density. If more number of s electrons are there in its valence shell, the isomeric shift value will be least. If least number of s electrons are there, then isomeric shift value will be higher. And now we are going to see the what are the nucleus they have given. So here they have given Fe2. So Fe2 means 4s0 3d6. Next, Fe3 means 4s0 3d5. Next, Fe4 means 4s0 3d4. So it's not we cannot predict now because all s orbitals are having 0 electrons. So because of that reason we cannot predict the isomeric shift values from s electron density, because all are 0 0 0 electrons are there. Now here we have d electron density. From d electron density also we can predict the isomeric shift values. How? So here we will take shielding concept. So this is the nucleus. Here s electrons are there, so p electrons and d electrons. So here if the d electron density increases, so what will happen? The shielding on s electrons will increases. So automatically what will happen? S electron density will decreases. So if number of d electrons will increases in the valence shell, what will happen? This will shields the s electron density. That means the s electron density is increasing. So here we can write it as a isomeric shift is directly proportional to d electron density. Okay, so it's very simple. If number of d electrons are more, that means it will shields the s electron density. That means s electron density is decreasing. So here in case of Fe+2 there are 6 electrons, and in case of Fe+3 there are 5, Fe+4 4 electrons. So here we can see that the isomeric shift value of Fe+2 should be greater than Fe+3 than Fe+4. So the answer will be this. And the next question is, we have a To record the Mass-Baur spectrum of iron containing a samples, X is used. Now we know what is that X. See, whenever we are using an iron sample, the source which we will use is the 57 cobalt. The source which we will use, that is 57 cobalt. So the answer will be A, this one or this one. So X after nuclear transformation, Y gives a gamma radiation used in the Mass-Baur spectroscopy, and X and Y are respectively. So here we can see cobalt 27, 57. This list iron 26, 57 in the excited state, and further it goes into the ground state. Okay, so if beta particle emitted, so what will happens? The mass number will increase and atomic number will no change. So here we can see that the mass number is no change. Here mass number will increase by 1 unit, right? For beta particle. So here mass number is not increasing. So atomic number is decreasing by 1 unit. That means that is K electron capture. When K electron capture happens, that time atomic number will decrease by 1 unit and there is no change in the mass unit. So here we have a iron 2757. So through the K electron capture, it forms iron 2657 in the excited state, and further it goes into the ground state. So here answer is cobalt 57, and this is by the K electron capture. The next question we have here, in the Mass-Baur spectrum of iron cobalt 5 recorded in the presence of magnetic field, the original spectrum with the 2 lines changes into 1 with. So iron 57 having a 2 spin, one equals to 1 by 2, another one equals to 3 by 2. So when we place iron 57 in the magnetic field, so we kept iron 57 in the magnetic field. When you kept like this, so there will be an interaction between the nuclear spin of iron with the magnetic field. So there are 2 spins for iron. We have 1 by 2 in the ground state and 3 by 2 in the excited state. When we will keep when we will keep this iron 57 in the magnetic field, this nuclei will interact with the magnetic field, and further this will splits. Further this will splits into minus 1 by 2 plus 1 by 2, and 3 by 2 will split into 4 lines. Minus 3 by 2 plus 3 by 2 plus 1 by 2 minus 1 by 2 minus 3 by 2. So originally when we recorded the Mass-Baur spectrum of FeCO5, where source equals where nuclei is 57 iron, that time we got only 1 line spectrum. So here after keeping in the magnetic field, what is happening? There is a splitting is happening. So finally we will end up with the 6 lines. The selection rule in the Mass-Baur spectrum equals to 0 or 1. Delta MA equals to 0 or 1. So there will be a transition from the ground state to the excited state. So we can see this transition, and this difference will be equals to 1, and we can see this transition, this difference will be equals to 0, and we can see transition from here to here, this will be difference will be 1, because minus, so plus 1 by 2 minus 1 by 2, this will be 1, and from here to here also it will be equals to 1, and then there is, this cannot be 1, plus 1 by 2 minus 1, no, this cannot be 1, so this transition is not allowed. And now there is 3 transition from this state, similarly from here also 3 transition. So from here to here 1 transition, here to here another transition, and here to here another transition. There are 6 transitions are possible. Here we just need to see that. So we have, let's say we are taking this transition, minus 1 by 2 minus 3 by 2. So this difference will be equals to 1. So because of that, because here selection rule delta ma equals to 0 plus or minus, because of that this transition is allowed. So originally we have a 2-line spectrum without magnetic field. So when we will keep in the magnetic field, that will convert into 6-line spectrum. So here 6 is the answer. Next, among the following, those act as a magnetic Mass-Baur nuclei. So we know that here iron is Mass-Baur active, okay, and tin also Mass-Baur active. What about 57 cobalt? 57 cobalt is not Mass-Baur active, but the source, we can use this one as a source, but it cannot be active in the Mass-Baur spectra. So here by elimination method we can remove this answer, remove this answer, remove this answer, because in every way 2 is there. That is 57 cobalt. 57 cobalt we will use as a source, but it cannot be magnetic nuclei active, sorry, Mass-Baur nuclei active. So because of that we will remove these 3 options. The only option is left is this 135. So iodine 129 also active in the Mass-Baur spectrum. And next question about the recoil energy. So recoil energy is very important concept. So here we have one principle. So here they have asked, in the Mass-Baur spectrum, source emitting at 14.4 kilo electronic volts had to be moved towards the absorber at 2.2 millimeter per second inverse for resonance. The shift in the frequency. So here one principle is there, that's very easy. Shift in frequency delta nu equals to nu v by c. So here v equals to velocity by which source is moved. Next, c equals to velocity of light, and nu is the frequency. So frequency as given, that is equals to 3.48 into 10 to the power of 18, and then the velocity by which source is moved, that is equals to 2.2. This is 2.2, and velocity of light we know that is constant, 3 into 10 to the power of minus 11. So we just substitute these values, 3.48 into 10 to the power of 18 into 2.2 by 3 into 10 to the power of 11, and the final answer will be 25.5 megahertz. So these are the some questions they have asked from the Mass-Baur spectrum in the previous years. Thank you.